Okay, Assalamualaikum and good afternoon. Hi everyone. Today in this session, I'm going to share with you on how we can solve this problem. So this problem P-4-1 comes from Chapman's book, and this is the problem related to SC machinery fundamentals, which is we have been talking about the SC machinery fundamentals in our third topic, which is topic 3. So this is basically represents the tutorial 3.1 for topic 3, which is SC machinery fundamental. So we have this particular wire loop. Okay, this particular wire loop which is rotating in a uniform magnetic field shown in this figure. As you can see in this figure, we have this wire loop, and this wire loop is rotating mechanically. Okay, omega m is mechanical rotation. Okay, so it is rotating counterclockwise direction, and we have this particular permanent magnet that providing the uniform magnetic field from north to south. Okay, so we have the direction of the permanent magnet vector here. Sorry, the intensity of the B, which is magnetic field of this particular permanent magnet that represent the stator of the machine. And then we have this wire loop that represents the rotor. Okay, so given that B is 0.5 Tesla to the right direction, R, which is the radius of this wire loop, okay, from the center to any direction, to the left direction, which is R, to the right direction is also the R from the center. Then okay, R is 0.1, and then L, which is the length of the segment. Let's say this B segment, the length of the B segment is L, which is 0.5. Similarly, at the C segment also we have L, which is 0.5. And then the mechanical speed, rotational speed, angular speed of this machine is 103 radian per second. So that all of the values has been given. So we want to find the first one. We want to calculate the voltage E dot induced in this rotating loop. Okay, before we go to the first question, let me just redraw this particular figure. So we have okay, this is tutorial 3.1. So we have north permanent magnet and then south permanent magnet. Then we have this particular wire loop, which is the A and B segment here, like that. So let's say the right hand side is AB segment, the left hand side is CD segment. All right. So this particular wire loop in a uniform magnetic field, direction of the magnetic field is from the left to the right, like that. Let me just roughly put it like that. And then this wire loop is rotating counterclockwise direction. Different color. This wire loop is rotating counterclockwise direction. That is omega. Okay, so we have that particular illustration, and given that B is 0.5, and then we have R is 0.1, L is 0.5 again, and then omega is given as 103 radian per second. Let me just ignore the units here that is already being given in the question, right? So we have this, all of the values given. We want to calculate the E dot. Okay, so for this particular wire loop, if I can redraw this into a wire loop like this, okay, suppose that we have AB segment, CD segment, like that. Then we rotate this wire loop counterclockwise direction. All right, and then okay, so we know the direction of rotation, meaning that we can represent by V, right? V is the direction of the rotation, which is the speed, angular speed, okay? Sorry, the tangential speed of this particular wire loop lah. So, and then similarly, we can draw B. Let me just use the red color again. B is to that direction. Okay, imagine that B is to that direction. So, if we use our right hand rule, okay, we use our right hand rule to determine the we use the left hand rule to determine the induced voltage using this figure. Okay, using this figure, we use left hand rule to determine the voltage for this particular figure. Okay, we use the left hand rule. Induced voltage direction supposed to be in which direction? So we have V, our thumb, B is our index finger, our middle finger, and then our index finger is induced voltage direction. Let we apply this, okay, the left hand rule to this particular figure. So we have V, B, and then supposed to be like that. Okay, so in this case, we can say that V cross B. Okay, so the induced voltage for this particular figure is to that direction. All right, so this is the induced voltage, meaning that this is positive, that is negative. Okay, for segment AB, induced voltage is to that particular direction. This is E in, meaning that that particular direction is the induced voltage. And then similarly, we can do the same thing to determine the induced voltage for CD segment, which is B is still the same direction, that direction, and then induced voltage supposed to be in that direction. So this is E in for the CD segment. All right. So basically, we know that the induced voltage is for AB is to that direction. CD is to that direction. Of course, at the terminal, supposed to be E dot or E in. At the terminal of this wire loop, supposed to be to that direction. All right. Okay. So that is the thing that we should understand before we start calculating. All right, we should understand the direction of induced voltage, because after this we are going to calculate the induced torque as well. So we will start with question A. Okay, calculate induced voltage. Let me just rewrite the question again. Calculate the voltage E dot induced in this rotating loop. Okay, so if we want to calculate the induced voltage for this particular simple loop in a uniform magnetic field, we can just refer to our lecture notes. Okay, in this particular slides of lecture note, we know that the induced voltage is 2R omega BL sine omega T. Okay, so induced voltage will be 2R omega BL sine omega T. Okay, so we can use that using the values that has been given. So we can just substitute all of the values that has been given. So 2R is 0.1, omega is 103, B is 0.5, L is 0.5, and then sine omega T. Okay, so we know that in this particular instant, the induced voltage during that rotation, omega M equals to omega electrical, and then it is 103, right? Okay, so we can just substitute sine 103 t. Okay, so that is the induced voltage for this particular wire loop inside the uniform magnetic field. Then we can further calculate this. We get 5.15 sine 103 t in volt. So that is the answer for the first, for A, right? And then question B, suppose that we have 5 ohm resistor connected as a load across the terminal of the loop. Calculate the current that would flow through the resistor. So we know that induced voltage E thought is the induced voltage, which is 5.15 sine 103 t. Then we calculate the resistor of the value of 5 ohm to that terminal, which is something like this. We have this wire loop, then I connect this resistor, and this resistor is 0.5 ohm, right? So across this we have E in, okay, equals to that, right? So basically we can just calculate the current I is E in divided by R. So E in is 515 sine 103 t divided by R, which is 0.5. Okay, sorry, R is 5. Okay, so we get current, which is 1.03 sine 103 t. This is the current in ampere. So for B, we get the value of the current already. Then what is the question for C? The induced torque. Calculate the magnitude and direction. We want to know the magnitude and direction of induced torque. Okay, calculate magnitude and direction of the induced torque on the loop for the conditions in B. For the condition in B, meaning that once we connect the resistor of 5 ohm. All right. So now we can always refer to the lecture notes, the equation for the torque induced. Right. Torque induced is 2 RILB sine theta. So torque induced is 2 RILB sine theta. Okay. Alright. So we can do the same thing for the question A, which is we just substitute all of the values given in the equation here, which is 2 R is 0.1, I is 103 sine. I'm going to use omega t. Okay, I'm going to use omega t, which is at this instant. Okay, we know that it is 103 radian per second, but in this case I'm going to use omega t because actually we want to use the new variable, because once we connect resistor, there will be current will be flowing, and then at that time we don't actually sure that is it 103 radian per second? We are not really sure. So I just put omega t right over there for the current. All right. Then substitute L 0.5, substitute B 0.5. So and then finally sine theta. Theta is now also the omega t. Okay. Theta is now also omega t because once the torque experienced by that wire loop, we know that the new angular speed is omega, so theta also omega t. Then we can further calculate this torque to the final answer of this torque is 0.0515 sine square omega t. Okay, torque is Newton meter. We write down the unit. Now, we are going to determine the direction of the torque. So, let me just redraw again this particular figure, alright? Okay, so let's say this is our wire loop, alright? We know that we rotate this wire loop counterclockwise direction, CCW, okay, at omega m, right? So we rotate this counterclockwise direction, and then since this wire loop is inside the uniform magnetic field, what happened to the AB segment and CD segment is the voltage will be induced. So the direction of the voltage induced, we can draw it like this, okay? Sorry. So at segment AB, that is the direction of the induced voltage. At segment CD, that is the direction of induced voltage. Okay, we know that. So what happened in question B was I connect 5 ohm resistor. Now I connect 5 ohm resistor to this terminal that induce the voltage. We have this voltage induced. We have this voltage induced. Okay, I connect the resistor. So what happened is the current will be flowing. In which direction of the current? Okay, the current will be flowing from positive to negative. Okay, from positive to negative. Let me just redraw. You can check this figure. Okay, I'm going to draw the current that is flowing inside this wire loop. Okay, start from the resistor here to that direction, and then back to the resistor, meaning that the direction of the current is that direction. Okay, now we want to know the torque direction, the induced torque direction, whether it is the clockwise direction or counterclockwise direction. We know that initially the wire loop was rotating counterclockwise direction that induced voltage. Once we connect the resistor, the current will be flowing in that closed loop, because in a complete circuit, complete circuit like this, when we attach resistor across this induced voltage terminal, okay, current will be flowing lah. When we have this closed loop, we have this sort of complete circuit like this. Okay, so once we have current flowing in this wire loop, since this wire loop also placed inside, which is inside the magnetic field, what happens is the torque will be induced. Then we have already calculated the torque in our C question. So we have already know the magnitude. So this is basically the magnitude of the torque. Now we want to determine what is the direction of the torque. We can simply use this right hand rule. Okay, use right hand rule, all right, to determine direction of the torque. How do we use this? F I L cross B. So we know the direction of the let me just use different color. I'm going to use purple, right? Let's say in the segment AB here, the direction of the current supposed to be that direction. Okay, then the direction of the magnetic field supposed to be that direction lah. This is perpendicular. This is B, this is I. So what is the direction of the force? Okay, what is the direction of the force? Okay, using the right hand rule. Okay, I B sky I B I F. Middle finger is B. Okay, middle finger is B. Which is quite just pause. So middle finger is B, supposed to be it's like this. Okay, that means if you apply this right hand rule, or I cross B, we know that I cross B, I is that direction, B is that direction, I cross B. Okay, suppose F it is to that direction, F to that direction, which is the direction of the torque. So in this particular case, we can just draw the torque direction which is to that direction. Like segment CD supposed to be different opposite direction. So this is the torque at segment AB, and that is the torque at segment CD. So in this particular example, we know that the torque direction is also the same as the initial rotation, which is counterclockwise direction. Torque is, that is the magnitude, and the direction is direction of torque is also counterclockwise direction. Okay, so that is for C. All right, now D, calculate the electric power. Calculate power being generated by the loop for the condition in B. Okay, if we want to calculate the electric power, whether we can calculate the instantaneous power PT or the average power. So basically in this particular question, we want to calculate the instantaneous power. All right, okay, so to calculate the instantaneous power, basically we can use PT equals to E in times I. So we know that E in is 5.15 sine, I'm going to use omega t again in this case. I is 1.03 sine omega t, which is 5.3 sine square omega t. That is the power. Okay, power, instantaneous power in watt for that particular example, right? Okay, so how to calculate average power? So basically, you can always check on the Google to the average, about the average power. You can always check in the Google. So the average power is determined as P average. Average is Vm peak voltage, Im peak current, cosine phi, and then integration of sine square omega t dt divided by 2. Okay, so in this particular example, we know that this particular part is 1. Sorry, this particular part is half. Is half, right? So this particular part is half. Let me just have a check. Not T, that is T, not 2, right? So this particular part is half. So actually the average power is VMIM cosine phi divided by 2. So that is the average power. So for this particular case, so basically in my question for test, for exam, for example, basically what I'm going to ask you is to just determine the instantaneous power. But in this case, let me just show you on how you can calculate the average power. Okay, for this particular case. Okay, if you like to calculate the average power, you can use P average. We do the integration for t, which is for all t, right? Let me just show this example. Sin square dt, right? So this is the instantaneous power, all right? So we integrate that instantaneous power for all t, for all the period t. Let's say for this particular t in one cycle, which is 0 to 2 pi, all right? Okay, 1 over t. Let's say this t is from 0 to 2 pi. Okay, all right. So I want to get rid of the some constant here. I put 5.3 outside. Then t is now 2 pi, right? So 1 over 2 pi from 0 to 2 pi. Okay, sine square omega t dt. Okay, so this particular part of power is half. Why? Because you can see that in this our Google, we have Google just now, that this particular part 1 over t integration of 0 to t sine square omega t dt, this is the power average, which is half. Alright, this particular part is half. So in this case also, this is very similar to that previous one. So this part is half, meaning that for this particular case of calculation, we can say that the power is about half of the instantaneous power, meaning that we have that sort of power, instantaneous power. So the average power is supposed to be half to that. Let's say this is example here, the power, instantaneous power, and then if you want to get the average power, supposed to be this is the average power. So the average power in this case is 5.3 divided by 2, which is 2.65 watt. So that is the example calculation of the average power. I just show you, okay, to let you know, just we can use we can either calculate the instantaneous power or average power. Okay, okay, I'm going to solve question E now. Calculate the mechanical power being consumed by the loop for the conditions in B. How does this number compare to the amount of electric power being generated by the loop? Okay, so we are going to calculate mechanical power. Okay, mechanical power, which is in question E. Mechanical power being consumed by wire loop for the condition in B. Okay, so we can just calculate using P max tau omega. So even though we didn't see any of this equation in our discussion on topic 3, but basically in the beginning of the lecture, we have already discussed in topic 1 introduction that mechanical power is equals to tau omega, right? So we can use that equation. P is tau omega. Then we know that the torque induced is 0.0515 sine square omega t. So in this case, let me just again use the 103 as the omega. Okay, then we can easily get this sort of answer. So what we can observe from this answer is 5.3 sine square omega. What that means, okay, mechanical power being absorbed by the wire loop is the same as the electrical power. So we have got the electrical power, the instantaneous power, instantaneous electrical power, which is this one, 5.3 sine square omega t. Also, the mechanical power is 5.3 sine square omega t, meaning that we can say that P max equals to P elect equals to 5.3 sine square omega t. Okay, so we can conclude that this machine, okay, this machine is acting as a generator that convert mechanical power to electrical power. Okay, that's it. So that is the answer for E, and then we have already finished discuss this too. So I am going to close this up to this time. So okay, that's all. Thank you.